Hi, and welcome back. The version of the Smith-Waterman algorithm that we have designed and benchmarked has been executed for both our target architectures on our local servers that are equipped with the two FPGA devices that we have considered. However, owning and maintaining a computing infrastructure requires to consider multiple unknown factors such as replication of data, redundancy, latency, and recovery in case of damage. For all these reasons, nowadays companies and application developers prefer to use cloud infrastructures such as the one offered by Amazon Web Services or AWS. In these regards, AWS recently released a new type of computing instances called EC2 F1, equipped with FPGAs. This service, known as Infrastructure as a Service, allows users to use FPGA devices on the cloud without worrying about maintaining a computing infrastructure or buying an FPGA device. It is possible to use the AWS F1 instances with a Hardware Developer Kit, or HDK, and with an FPGA Developer AMI. The latter is a kit that helps the developer in the process of designing the hardware accelerator. It includes code samples, debug interfaces, and many other tools to ease the process of developing FPGA code for your F1 instances. The kit is accessible in the AWS FPGA public GitHub repository and is mainly used to facilitate RTL development of an AFI or Amazon FPGA image. The FPGA AMI, from the other hand, is a CentOS image with already installed Xilinx SDXL framework. To start designing a hardware architecture, an FPGA device using SDXL, it is necessary to select one of the available computing instances and start the design process. AWS, in fact, provides multiple and different computing instances, where the differentiating factors are computational power, networking capabilities, and memory. Furthermore, although it is necessary to have an F1 instance running to execute on the FPGA, it is not necessary this particular compute instance to design and emulate our design. It is possible to select a computing instance with different power, depending on user needs. In order to execute our binaries on the FPGA provided in the AWS infrastructure, it is necessary to generate an Amazon FPGA image. Using a script contained in the AWS FPGA repository, it is possible to register the FPGA image starting from the Excel bin file. The result of this operation will generate a AWS XCL bin file and will register the binary for the FPGA. In this way, it is possible to start an F1 instance and run the binary on the FPGA device. The F1 instances are equipped with Xilinx UltraScale Plus VU9P FPGAs, fabricated using 16 nanometers technology, 64 GB of memory and 4 DDR4 channels, a X16 PCIe Express interface with the processor, approximately 2.5 million logic elements and 6800 DSP engines. These devices are bigger than the previous we used. Here there is a comparison among the three different FPGAs. Look at the number of logic cells, flip-flops and LUTs among these three devices. The VU9P is very huge. It has more than 3 times the number of logic cells of the KU3, more than 2.5 times the number of flip-flops than the Virtex 7, and almost 4 times the number of LUTs of the Kintex. The huge area of this FPGA offers the possibility to obtain a high level of parallelism from the application we want to accelerate. Considering the number of logic cells, flip-flop and LUTs, you can observe as the VU9P is a very huge FPGA, offering a very high level of parallelism. But that is not all. On AWS, it is in fact possible to work with an instance with just one of these FPGA, that is a F1 2x large, or it is possible to ask for an F1 16x large instance, containing 8 VU9P FPGAs that can execute in parallel. This is awesome, right? Now, I will stop with this introduction to AWS, and we see how to execute the Smith-Waterman we have designed so far on a single FPGA F1 instance. I will assume that you already registered to AWS, and I will show you, in the next lessons, how to use SDXL on these instances both using the GUI and the makefile flow. Then we will generate the XCL bin as we did before when we were on our local servers, and finally, we will use the scripts provided in the AWS FPGA GitHub repository to register the Amazon FPGA image, or AFI, and generate the AWS XCL bin. For all the steps concerning the generation of the XCL bin, we will not use an F1 instance, as this is quite expensive. We will in fact use other instances available in AWS that are able to deliver a reasonable amount of performance at a lower price. Then, once our AFI will be registered and available to be used within the infrastructure, we will ask for an F1 instance and we will run our AWS XCL bin on the Xilinx UltraScale Plus VU9 pin FPGA.